Hello, welcome to my talk, all about fluid. This talk is the second part of the talk on whether the Navier-Stokes equation is correct, and this part would be for solution on how we can better formulate the fluid viscous stress tensor based on the solid physics, how we can derive the correct Navier-Stokes equation using the newly defined fluid viscous stress tensor, and how we can solve those inconsistencies I have talked about in the first part. Let's first have a look at the inconsistencies behind the Navier-Stokes equation, and then I will show you how we can solve those inconsistencies via a new fluid viscous stress tensor, and how we can better derive the Navier-Stokes equation. As we have shown in the first part of the talk on whether Navier-Stokes equation is correct, there are 4 inconsistencies identified in that talk. These inconsistencies include: the classic Couette flow has shown that the shear stress are asymmetric for fluids. There exists viscous stress in the pure rotation motion of fluids. Therefore, the ignorance of the viscous stress due to the rotation motion would not be physically consistent with the fact. The original form of the symmetric stress tensor had an artificial factor 2, and the explanations to this factor in some famous reference books. It is merely used for a purpose of convenience, but there is no physical basis to support it. In real flows, there have been found exceptions for the Couette symmetric stress tensor. The question is, why do we have exceptions for the universally correct laws? The key is the formulation of the fluid viscous stress tensor. It is asymmetric, not necessarily limited to be symmetric. As for whether the asymmetric stress tensor could cause a spinning motion in fluid, the answer is no. For instance, if we look at this fluid element and apply the shear stress tau to 3, and this shear stress can simply cause a flow as seen in this figure. This is fundamentally different from the solids. As we know from the Newton's definition of fluid friction or stress, the fluid viscous force or stress is caused due to the different fluid speeds at 2 joint spatial locations. Therefore, we can examine 2 neighboring points in the fluid, A and B, and the relative fluid velocity of B with regard to A at a certain time is started here. For the point A, its position and the velocity are given as this, and B, the location and the velocity are given as this. So the increments are given as delta x, delta y, and delta z in the position, and for the velocity, it is delta u, delta v, and delta w. Based on the chain rule of differentiation, we can calculate delta u as this. Here, the velocity u is the function of the independent special variables x, y, and z. Similarly, we can calculate the velocity increment delta v and delta w in y and z directions. Put all this together, we can calculate the relative velocity of point B with regard to the point A as this. And this can be written in the matrix form as this. Here, the matrix, it's actually a tensor. And from this formulation, we can define the tensor A double arrows as the strain rate tensor. And this tensor is correct for all fluids, including Newtonians and non-Newtonians, because this formulation is simply from the direct physical analysis without assuming the fluid types in the analysis. By analog to the definition of Newtonian fluid viscous stress, it is proportional to the rate of strain, like tau xy equaling to the fluid viscosity timing the gradient of the velocity u with regard to y. Therefore, based on this principle, we can construct the general fluid viscous stress tensor as this for the Newtonian fluid. This formula is correct for the isotropic fluid because we assume mu is isotropic and constant for representing the fluid viscosity. For a more general expression for the fluid viscous stress tensor, it can be simply expressed as this. Here, the stress tensor can be asymmetric. Therefore, with the newly defined asymmetric stress tensor, we can see the relative velocity between two neighboring points is from the direct physical analysis. Thus, it is universally correct. The symmetry for the stress tensor is not required for the real stress tensor for fluids. It is because the shear stress will simply cause a flowing motion rather than a spinning motion in fluid. The shear stress directly follows the definition of Newtonian viscous stress, which is physically correct for Newtonian fluid, and this can be easily adopted for the non-Newtonian fluids if the fluid stress is calculated for the actual fluid. The moment equation for fluid motion is based on the Newton's second law of motion, which can be simply expressed as this for the fluid. Here, scalar v is the volume and vector v is the fluid velocity. This part is the time rate of change of fluid momentum. This part is the body force, and this is from the surface force. So basically, this equation is the Newton's second law of motion. The time rate of change of fluid momentum equals to the total force acting on the fluid. By applying the Gauss divergence theorem, we can change the surface force of the integral on the fluid surface into the integral on fluid volume as this. So we have the equation for the fluid momentum as this. Based on this moment equation, we can see here the capital D in the differentiation means the substantial derivative. However, the derivative of the volumetric integral on the whole fluid with regard to time would make no difference whether this is substantial derivative or the normal derivative, since the volumetric integral on the whole fluid domain is a function of time and the volume, but it is independent of the special variables x, y, and z. This is why, in this expression, the substantial derivative is the same as the normal derivative. However, for calculating this term, we need to employ the Reynolds transport theorem as this. Here, we can assume F0 equals to null vector V. Applying the Reynolds transport theorem, the left-hand side of the equation would become to this, and then we can obtain the integral moment equation for fluids as this. So from this integral moment equation, we can easily obtain the differential moment equation for fluid expressed as this. Here, rho double vector V and T double arrow are both tensor. So following Stokes, the total tensor is given as the combination of the tensors due to the pressure by this term, due to the fluid compressibility by this term. Here, lambda is the second viscosity coefficient, and due to the viscous stress tensor. The only difference from the conventional derivative of Navier-Stokes equation is the shear stress tensor. Here, the shear stress tensor is defined by this component. It can be seen the stress tensor is an asymmetric tensor. So if we apply this to the moment equation for this total tensor, the divergence of the total tensor is calculated as this. It's a vector. Here, we are going to examine the last three terms in the first row of the total tensor's divergence. And we use the definition for the asymmetric stress tensor. So we have this, and it can be rated this and this. Similarly, we can have the equation for the last three terms in the second row, and the last three terms for the third row. We have all this, and then the divergence of the total tensor can be written as this. For deriving Navier-Stokes equation, we considered the genetic form of the Navier-Stokes equation here. First, the continuity equation is given as this in vectors, and it can be written as this using the Einstein summation form. The moment equation from the Reynolds transport theorem given as this. Using the Einstein summation, we can write the moment equation as this. So, for the divergence of the double velocity vector, it is calculated as this. And combine this with the continuity equation, we can obtain the genetic Navier-Stokes equation as this. Here we can see the substantial derivative in the square bracket, and this universal Navier-Stokes equation is same for both compressible and incompressible flows. In this slide, we are going to look at the incompressible flows, where the flow density is a constant and the continuity equation is given by this. Now look at the divergence of the total tensor. So we can drop the fluid compressibility term. Thus, we have the moment equation in x direction and in y direction, z direction as this. So if we write this back into the vector form, we have the Navier-Stokes equation for incompressible flow as this. Now for compressible flow, the continuity equation is given as this. Again, we look at the divergence of the total tensor. Here we have to keep the compressibility term. However, the second viscosity can be assumed reasonably as lambda equals to 1/3 of the fluid viscosity. This can be understood that in the fluid dynamic equation, we have used the fluid compressibility 3 times, as we can see in this total tensor. Therefore, it's reasonable to evenly distribute the contribution. So, that's why we have the 1/3 of the viscosity. By comparison, the Stokes assumption, given the second viscosity coefficient lambda equals minus 2/3 mu. However, this is still very controversial. This can be seen from the book Aerodynamics for Engineering Students. So if we apply this assumption, lambda equals 1/3 mu, we can get the moment equation for the compressible flow as this. Here is the term for the fluid compressibility. We can write back the moment equation into the vector form. We have this. This is exactly the same as the moment equation in the conventional Navier-Stokes equation for compressible flow. We are going to solve all these inconsistencies we found for the symmetric stress tensor for fluids. The first solution would be for the shear stress in Couette flow. For such a laminar flow, the velocity distribution is given as this. And based on the newly defined stress tensor, we can calculate the horizontal shear stress as this. Tau 12 is non-zero. This is understandable since there is a horizontal flow in Couette flow. And we can also calculate the vertical shear stress, tau to 1 equals this. It is 0. This is also correct since there is no vertical flow in the Couette flow. As such, the first inconsistency is solved. For the second inconsistency, we will look at how the rotation motion is included for contributing to the fluid viscous stress. The asymmetric strain tensor T double arrow can be separated into 2 parts, the symmetric part and the anti-symmetric part as this. in the conventional derivation of Navier-Stokes equation, the symmetric part, which represents the shear deformation of fluid, was used in deriving the Navier-Stokes equation. And these are the symmetric stress. But the anti-symmetric strain rate tensor, which corresponds to the rotation of fluid, with omega defined as this, but this has been dropped in the conventional derivation of Navier-Stokes equation because the rotational motion was believed to make no contributions to the viscous stress in fluid. But this is not correct. For fluids, the pure rotational motion will cause the stress. So, if this asymmetric stress tensor is used, the contributions from both fluid shear deformation and the fluid rotation would be included automatically. Therefore, the second inconsistency is solved by using the newly defined asymmetric stress tensor. For the third inconsistency, if the newly defined asymmetric stress tensor is employed, we can derive the Navier-Stokes equation directly, as we have shown in the previous slides in this talk. The asymmetric stress tensor is given by this. Here, Aij is the asymmetric rate strain for the fluid, defined as this. Unlike the original derivation of Navier-Stokes equation, in formulating the symmetric stress tensor for Navier-Stokes equation, an artificial factor 2 must be employed as this. Here, Sij is the symmetric strain rate component, which represents the shear deformation for the fluid element. Based on the famous textbooks, the explanation of the artificial factor 2 is merely used for convenience. More specifically, it is used to cancel out the factor 1/2 in the symmetric strain rate expression. Otherwise, the derivation of Navier-Stokes equation would not be correct. Therefore, by employing the newly defined asymmetric stress tensor, the artificial factor would not be necessary. Hence, it would be more consistent with the real physics in the formulation. And thus, the third inconsistency is solved. The fourth inconsistency is for some exceptions for the symmetric stress tensor. In the book of Kondo, Cohen, and Dowling, Fluid Mechanics, it mentioned one exception. For the electrolyzed fluid, the symmetry of the stress tensor is violated, and for the analysis, the anti-symmetric part must be included. So if we look at this asymmetric stress tensor, we can see it includes the symmetric part and the anti-symmetric part automatically. Therefore, this asymmetric stress tensor automatically includes the anti-symmetric stress tensor. In the Wilcox book, Turbulence Modeling for CFD, it is mentioned the symmetric stress tensor is not for the anisotropic flow. This requirement can be achieved by using the asymmetric stress tensor, either for Newtonian fluids or for genetic fluids. Use genetic stress tensor, even for the anisotropic flow, because the asymmetric stress tensor has no requirement on the symmetry on the stress tensor. Thus, this asymmetric stress tensor could provide more flexibility for constructing the fluid viscous stress tensor for both Newtonian and the genetic flows, including those anisotropic flows. So in this slide, the summary is given for the correctness of Navier-Stokes equation. The talk for better understand the fundamentals and the issues with the Navier-Stokes equation, so to provide better physics for understanding the equation, rather than to prove the incorrectness of Navier-Stokes equation. To distinguish the difference of the motions for fluids and solids, the flowing motion in fluids causes the fundamental difference between the fluid motion and the solid motion. To solve the inconsistencies behind the Navier-Stokes equation, there are conflicts between the requirement of the symmetric stress tensor and the definition of fluids. The newly defined asymmetric stress tensor is the key. To formulate the mathematical equation and the viscous stress tensor are all based on the solid physics. There is no artificial factor or parameters in the formulation, and all formulations have sound physical foundations. To provide the flexibility for fluid motion, there is no requirement or limit for the fluid stress tensor, which can be either asymmetric or symmetric, totally depend on the actual flows. It is hoped that such an flexibility could provide the new possibilities in turbulence modeling, since we are no more limited on the symmetric stress tensor.